Example 4. We're asked to solve the following rational inequality algebraically. So we know when we're solving a polynomial or rational inequality algebraically, that's going to clue us into sign chart. So we need to know that the algebraic method is to make a sign chart. Okay, so to get us to that sign chart, our first step, we need to rewrite this so we have a 0 on the right side. So we're going to have to subtract 1 from both sides. So we'll have 4x plus 1 over x minus 1 minus 1 less than or equal to 0. Now, since it's rational, we now have to combine the left side, combine the function into one single quotient or one single fraction. So we're going to need to subtract that 1. So if we look at that as 1 over 1, we can rewrite the 1. So we'll rewrite here 4x plus 1 over x minus 1 minus, and we'll express the 1 as x minus 1 over x minus 1 because the least common denominator of these two would be x minus 1. So if we write these with the same denominator, now we can subtract. So we can subtract the numerators, and don't forget to subtract both terms in this fraction. It's not just the x that's subtracted, it's the negative 1 as well. So if we subtract, we'll get 3x plus 2 over x minus 1 is less than or equal to 0. Now that the 0 is on the right, and we've expressed it as a single quotient or a single fraction, this is our function f of x. So we're looking for where f of x is less than or equal to 0. So that means we want the negative regions. So when we make our sign chart, their solution will be the solutions that contain the regions that contain the negative values. Okay, second step. We're going to solve this. We're going to solve the related equation. So it's not an equation, but we're going to solve it as if it is an equation so we can find the zeros. So I want to solve 3x plus 2 over x minus 1 equals 0. So different ways we could do this. We know we could multiply both sides by the least common denominator, which would be x minus 1, to clear out that fraction. Or we know that if a fraction equals 0, the only way that could happen is if its numerator equals 0. So we could also just set the numerator equal to 0. Either way, we'll get to the same place. 3x plus 2 equals 0. So if we subtract the 2 and divide by 3, we have x equals negative 2/3. So the 0 of this function is negative 2/3. So that's going to go on our number line. But since this is a rational function, we also have to put on the number line any values that are excluded from the domain, because obviously those will be excluded from the solution. So we look at the denominator. So this is the same whether you look at the original function or the rearranged function here. Both of those are going to have an excluded value of 1, since x minus 1 would equal 0 if you put in a 1 for that x value. So our excluded value is when the x minus 1 equals 0, so that's an x value of 1. So now we're going to make our number line. So steps 3 and 4. So we'll make our number line, and then we're going to do our sign chart right on top of that number line. So now we need to put the negative 2/3 and the 1. Those are the only values we need on our number line. So now we're going to divide the number line up into these regions. So we've got the region from negative infinity to negative 2/3, then negative 2/3 to 1, and then 1 to infinity. So I'm first going to test a point in the region negative infinity to negative 2/3. So I'm going to pick negative 2. So I want to find f of negative 2. So again, we could plug this in to the function, or we can go to our calculator and use the table. So here's our function, 3x plus 2 over x minus 1, and I can go to the table, and here's our x value of negative 2, and our y value is 1.3 repeating, so we can just round that to 1.3. But all that matters is that that 1.3 is a positive number. So this region is going to give us positive values. Now let's test between negative 2/3 and 1. Now 0 falls in here, so that would be the easiest point to pick. So if 0 ever falls in any of the regions, you definitely want to pick 0 in whichever region it falls. So we'll find f of 0. Again, we could use the calculator if we'd like. So f of 0 is going to be negative 2. So we'll label negative 2, and we care that it's a negative value there, so that region is going to be a negative region. And then finally, we want to test 1 to infinity, so I'm going to try 2. Again, these are just examples of points you could plug in. You guys can plug in any points in that region, as long as you show all of this work here, showing me that you're plugging in these function values. So when we put in an x value of 2, we get a positive 8. So this is a positive region of the graph. Now, since it's a less than or equal to, the rearranged function here is less than or equal to, we want the negative regions, so we know that this is a no, this is a no, but this is our solution. So we want this region between negative 2/3 and 1. Now we have to think about the boundaries. Negative 2/3 was the 0 of this function. So since it's a less than or equal to, we know the function will equal 0 at negative 2/3. So we're going to include that boundary by putting a bracket on the negative 2/3. But at the 1, remember 1 is an excluded value. So even though this is a less than or equal to, our function can never equal 1. That's an undefined value. So we always use a parentheses, on the excluded values. So you use the inequality symbol to determine the bracket or the parentheses on the zeros, but regardless, if it's an excluded value, you have to use parentheses on the boundary. So then our final step, we write this in interval notation. So we've got bracket, negative 2/3, comma 1, and close those parentheses. Now, if we want to check this on our calculator graphically, we know we'll be looking for the negative regions. So this would be where the graph is below the x-axis. So here's our function. If we go to a graph on a standard viewing window, we can see the branches, which we know are very characteristic of these rational functions. You can see some splits in the graph, which would indicate the asymptotes. But ultimately, we're looking for this region here where the graph falls below the x-axis, which certainly looks reasonable. It certainly looks like it could be from negative 2/3 to 1. So if it stops here at 1, which our solution suggests, there must be a vertical asymptote here, which makes sense because we know that the x value can never equal 1. That denominator, the 0 of the denominator, is 1. So we can make a little sketch. I would make a sketch here in your notes. Oops. So let's make a sketch here. So we know we need our vertical asymptote would be x equals 1. We saw that on the calculator, and we know from the equation that that would cause the denominator to equal 0. So when we sketch this, we know that that x value of 1, you'll have a vertical asymptote is here. And now we know, if we look at our function here, the degree of the numerator is the same as the degree of the denominator, so we know we're going to have a horizontal asymptote, and if we'll find it by taking the coefficient here divided by the coefficient here. So 3 divided by 1 is 3. So we're going to have a horizontal asymptote at y equals 3, which we also saw in the calculator. And now we're going to fit our graph in between the grid here. So we know we have a 0 at negative 2/3. So we'll approximate right here. So we've got a branch in this region. And then we have a branch, you can see from your calculator, we've got a branch in this region. So our solution to this inequality is when the negative regions where the graph falls below the x-axis. So we can see we have this piece right here is where the graph falls below the x-axis. So we can see that's from negative 2/3 all the way to 1, and we've got that vertical asymptote that's bounding it right here. So when you guys show your work on a test or a quiz, what I'll be grading is this sign chart. So you have to show that minimum. So you have to show the f of whatever x values you plug in, and then the y value that you get out, and then whether it's positive or negative, and you want the zeros on the number line, and then this final solution shaded.